Okay, in this lecture we're going to cover the second part of the fundamental theorem of calculus, which gives us a very simple way, or relatively simple way, to evaluate definite integrals. So you might recall from your Calculus 1 course that when a definite integral is first introduced as representing the area under the graph of some function on an interval, that it's defined in terms of the limit of a Riemann sum. So you're taking little rectangles to approximate the area under the graph of some function on an interval, and then you're using more and more rectangles of a thinner width to find the true area under the graph of a function. So this is the formal definition of a definite integral as the limit of a Riemann sum. But evaluating definite integrals in terms of Riemann sums is very tedious. So you might recall some examples that you saw in Calculus 1. It was very difficult to evaluate definite integrals in that way. So part 2 of the fundamental theorem of calculus gives us a very straightforward way to evaluate definite integrals by making use of antiderivatives. So let's start by stating the second fundamental theorem of calculus, and then we'll look at several examples to see how it works and review some rules for finding antiderivatives. So here's what the theorem says. If f is a continuous function on some closed interval from a to b, then the definite integral of that function, f of x with respect to x, over the interval from a to b, is given as the difference capital F of b minus capital F of a, where capital F is any antiderivative of the function little f. So in summary, what the second fundamental theorem of calculus says is to evaluate the definite integral of some function f of x, which would represent the area under the graph of that function on an interval from a to b. We can find any antiderivative of that function that we're integrating. Let's call it capital F. And then we would evaluate capital F first at the upper limit of integration, b. So we plug in b to our antiderivative. And then we subtract the value that we get for our antiderivative evaluated at the lower limit of integration, a. Now, a little bit of comment on some notation that we'll use throughout the semester. So that difference, f of b minus f of a, is typically denoted as follows. F of x, and then behind the function f of x, we have a vertical bar with subscript and superscript a and b. So this notation where we write a function f of x and then we have a vertical bar after it with the values a and b is used as a shorthand to denote that difference, f of b minus f of a. So we could also include that notation as part of our theorem statement. So this theorem says, well, instead of evaluating definite integrals in terms of the limit of a Riemann sum, we just need to find an antiderivative of the function that we're integrating. And as long as our function is pretty straightforward, we know how to find antiderivatives. And a little bit later in this course, we'll see different techniques for how to find antiderivatives of some more complex functions. So let's look at a few examples to review antiderivatives and see how this second fundamental theorem can be applied. So here we're told to evaluate the given definite integral. And in part A, we have the integral from 1 to 2 of 1 over x squared dx. Now recall that 1 over x squared can be rewritten as x to the negative 2 power. So something that we'll use pretty often throughout this course is the fact that if we have x to a negative power, let's say x to the negative nth, that's the same as 1 over x to the nth power. So in order to evaluate this definite integral using the fundamental theorem, we need to find an antiderivative of x to the negative 2. So using the power rule from Calculus 1, in order to find an antiderivative of a power function, we would add 1 to the exponent. So we would have x to the negative first, and then we would divide by that number, negative 1. So this would be an antiderivative of x to the negative 2 power. And recall, in general, once we have found an antiderivative, we could always add an arbitrary constant, let's call it c, to that antiderivative, and it would still be an antiderivative. So I have found the most general antiderivative of my function, and the fundamental theorem of calculus says once we find that antiderivative, we're going to evaluate it at the limits of integration, 1 and 2, and then take the difference in those values. So let's see what we have here. Simplifying a little bit, this expression, x to the negative first divided by negative 1, well, that's the same as just negative 1 over x to the first power. So recall x to the negative 1 is just the same as 1 over x, and then when we divide by the negative 1, it's the same as just taking the negative of that quantity. Then we have our arbitrary constant c, and we're evaluating from 1 to 2. So recall this notation says, well, we first take the upper limit of integration and evaluate our antiderivative at that value. So substituting x equals 2 into our antiderivative, we have negative 1/2 plus c. And then we're supposed to subtract the value that we get by substituting 1 into our antiderivative. So substituting 1 in for x, we have negative 1 plus c. So simplifying a little bit, let's see what we have. So grouping our constants together, we had a negative 1/2, and then we were subtracting a negative 1, which is the same as adding 1. So negative 1/2 plus 1 gives us 1/2. And then we had an arbitrary constant c, and then we're subtracting c. So our constants cancel, and we're left with simply 1/2. So one point that I want to make in this example is that for definite integrals, we do not explicitly need to write the plus c term when we find our antiderivative. So notice in my earlier work, when I found the antiderivative of this function, I included a plus c, an arbitrary constant, which gives me the most general antiderivative. But we've seen in our work here that for a definite integral, when I evaluate my antiderivative at the endpoints 1 and 2, and I take the difference, that this c and minus c will cancel. So I don't need the c there. And in fact, that will happen for any definite integral. If you add an arbitrary constant c on the end, when you subtract those two functions, that is the value of the antiderivative you get at the endpoints, that plus c will always cancel. So we don't need to write it explicitly in the case that we're working with definite integrals. Now, another way that we might justify omitting that plus c term is by looking at the statement of the fundamental theorem of calculus itself. So notice that one part of our theorem said that capital F could be any antiderivative of the function that we're integrating. So if we can use any antiderivative we want, let's use the antiderivative where the constant c is simply 0. Or in other words, we don't need to explicitly write the plus c. We can work with any antiderivative. So let's take the one where the constant c is 0. So either way that we prefer to think about this justification, the point that I want to make in this example is that for definite integrals, you do not need to write the plus c term when you're finding your antiderivative. So from this point forward, moving through the course, we will never write the plus c for definite integrals. So let's look at some other examples. In part B, we have the integral from 1 to 2 of 5x squared minus 4x plus 3. So the fundamental theorem of calculus says in order to evaluate this, we need to find any antiderivative of this function. So finding an antiderivative, well, we can use the sum difference rule for antiderivatives and find an antiderivative of each piece individually. So starting with 5x squared, using the power rule, an antiderivative would be 5x cubed over 3, or 5/3 x cubed, minus the antiderivative of 4x would be 4x squared divided by 2, or 4 over 2 gives us just 2x squared. And then plus the constant 3, well, the antiderivative of any constant is that constant times the variable that we're integrating with respect to, in this case, x. And we don't need to write the plus c because this is a definite integral. As we've justified, we can take any antiderivative, so let's use the one where c is 0, and then we will evaluate this antiderivative from 1 to 2. So let's see what we get here. Substituting 2, our upper limit of integration, into this antiderivative, we have for our first term 2 cubed, which would be 8, times 5/3, which gives me 40/3, minus we have 2 times 2 squared would be 8, and then plus 3 times 2 is 6. Then we subtract the value that we get by taking our lower limit of integration 1 and substituting into the same antiderivative. So substituting 1 in for x, we have 5/3 minus 2 plus 3. So let's see what we're left with. So usually for these definite integrals, our last step requires a little bit of arithmetic. So one piece of advice that I can give when working through these problems is try to group or simplify the terms based off what denominator they have. So for instance, in this example, let me start by simplifying everything that involves a third. So here I had 40/3, and then I was subtracting 5/3. So that gives me 35/3. And now let me group all of the integers or whole numbers together. So from this first term, I had a -8 plus 6, or -2. And then I'm subtracting a -2 plus 3, or subtracting 1. So my -2 minus 1 gives me a -3. And from here, we can find a common denominator to simplify. So here we have 35/3 minus 3, which would be 9/3. So that leaves me with 26/3. Okay. So let's look at some other ones. In part C, we have the integral from 1 to 2 of t to the 6th minus t squared over t to the 4th, dt. So here the function that we're trying to integrate or find an antiderivative of is a rational function, a quotient of two polynomials. Now we know from the quotient rule that the antiderivative of a quotient is not just the quotient of the antiderivatives. So the question becomes, well, how do we find an antiderivative for this function then? So in this example, we could split this quotient into two pieces. Notice that our numerator is the difference of two functions. So we could split this as t to the sixth over t to the fourth, and then I'm subtracting t squared over t to the fourth. And now, simplifying, the first term of my function, t to the sixth over t to the fourth, is simply t squared. And then I'm subtracting, I had t squared over t to the fourth, which gives me t to the negative 2 power, or 1 over t squared. So, finding an antiderivative of each piece now, I know that the antiderivative of a difference of two functions is just the difference of their antiderivatives. So for an antiderivative of t squared, I would have t cubed divided by 3, or 1/3 t cubed, minus t to the negative 2 power. Well, if we add 1 to the exponent, we get t to the negative 1, and then we're dividing by negative 1. So that will give me a positive t to the negative first, or positive 1 over t. And then this antiderivative, we're evaluating from 1 to 2. And again, notice because this was a definite integral, we did not need to write the plus c term. So let's see what we get. To evaluate this, we're supposed to first substitute the upper limit of integration 2 into my antiderivative. So I have 2 cubed, or 8/3, plus 1 over 2, or 1/2. And then we subtract the value that we get by substituting the lower limit, 1, into that same antiderivative. So that would be a 1/3 plus 1. So let's simplify. Grouping terms based off the denominator, we have an 8/3 minus 1/3, which would be 7/3. And then we have a positive 1/2, and we're subtracting 1. So 1/2 minus 1 is minus 1/2. And now using a common denominator of 6, we would have 14 minus 3, or 11 over 6, for our value of this definite integral. Okay. So let's look at some other ones. In part D, we have the definite integral from log 3 to log 6 of 8e to the x dx. So recall for exponential functions, in particular e to the x is its own antiderivative. And the constant 8 we can pull out in front of our integral. So we have a constant 8 times, well, the antiderivative of our function e to the x is e to the x, and we're evaluating this from log 3 to log 6. Again, here I did not need the constant of integration since this is a definite integral. So let's see what we have. We have a constant 8 out in front, and when I evaluate my antiderivative at the upper limit of integration, well, I have e raised to the natural log of 6, and then I subtract the value that I get by substituting in my lower limit of integration. That would be e to the natural log of 3. But recall that the base e exponential and the base e logarithm, or natural logarithm, are inverse functions. So e raised to the natural log of 6 is just 6, and e raised to the natural log of 3 is simply 3. So I'm left with 8 times 3 which is 24. Okay. So let's look at another one. In part E, we have the integral from 0 to 2 of x cubed minus 1 quantity squared dx. So this is a composite function that we're trying to integrate. And in general, integrate or finding an antiderivative of a composite function can be a little bit tricky. So how can we do this? Well, one way would be to think about the x cubed minus 1 squared as a product. Squaring x cubed minus 1 is simply multiplying x cubed minus 1 by itself. So now I'm trying to find the antiderivative of a product of two functions, and we know from the product rule that the antiderivative of a product will not simply be the product of the antiderivatives. So how can we handle this? Well, we can expand this product. So if we expand x cubed minus 1 by itself, multiplying our first two terms, we have x cubed times x cubed, which would be x to the 6th. Then multiplying our outer two terms, we have a negative x cubed. And then multiplying the inner two terms, we have another negative x cubed. So altogether negative 2x cubed. And then multiplying our last two terms, negative 1 and negative 1, we have a positive 1. And then we're integrating with respect to x. So we have, for our antiderivative of x to the 6th, a 1/7 x to the 7th minus the antiderivative of 2x cubed would be 2 over 4, or 1/2 x to the 4th, plus the antiderivative of 1 dx would be 1x. We don't need to write the plus c explicitly here. And then we're evaluating this from 0 to 2. So let's see what we get. Evaluating our antiderivative at the upper limit of integration 2, we have 2 to the 7th, which is 128, divided by 7, minus half of 2 to the 4th, well, that's the same as 2 cubed, or 8, and then plus 2. And then we subtract what we get when we evaluate this antiderivative at the lower limit of integration. So substituting 0 in for x, we have 0. So we're subtracting nothing here. So let's simplify a little bit. We have 128 over 7 minus 8 plus 2 is minus 6. So using a common denominator of 7, we have 128 over 7. 6 would be 42 over 7. So 128 minus 42 leaves us with 86 over 7. All right. So let's look at another one. Part F, we have the integral from 0 to pi over 2 of cosine theta plus 2 sine theta with respect to theta. So a little review for antiderivatives of our trig functions. The antiderivative of cosine theta is sine theta, and then we have plus 2 sine theta. Now the antiderivative of sine of theta is negative cosine theta. And then we are evaluating this antiderivative from 0 to pi over 2. So let's see what we have. Substituting pi over 2, or let me maybe simplify this a little bit first. I've got a sine of theta, then my 2 times negative cosine gives me negative 2 cosine theta, which we're evaluating from 0 to pi over 2. So evaluating this antiderivative at the upper limit of integration, pi over 2, we have sine of pi over 2, which is 1, minus 2 times cosine of pi over 2, which is 0. And then we're subtracting the value that we get by substituting 0 in for theta. So we have sine of 0, which is 0, minus 2 times cosine of 0, which is 1. So we have a negative 2. So simplifying, we have a 1 minus negative 2, which is the same as adding 2. So we have a total of 3. Okay. So let's look at a few other examples to finish out this section. In part G, we have the definite integral from 4 to 8 of 2 over x with respect to x. So if we want, we can factor out the constant 2, or pull the constant out in front of our integral. And we're left with the integral from 4 to 8 of 1 over x dx. Now, recall that the antiderivative of 1 over x is given by the natural log of the absolute value of x. So for our antiderivative, we have 2 times the natural log of absolute value x. And the fundamental theorem of calculus says we take that antiderivative and we evaluate from 4 to 8. So let's see what we're left with. We have a constant 2, and then we're multiplying by the natural log of, when we substitute 8 in for x, we have the natural log of 8, minus the value that we get when we substitute in 4. So we have the natural log of 4. So this would be the value of our definite integral, but if we want to simplify a bit, we can simplify this down to a single logarithm by making use of properties of logarithms. So in particular, recall that the difference of two logarithms that have the same base, in this case they're both the natural log, is the same as the log of the quotient of those values. So here we have 2 times the natural log of 8 divided by 4, or 2 times the natural log of 2. So again, this would be an acceptable answer, but we can simplify a little further if we use more properties of logarithms. So recall another property of logarithms, which says if we have a constant in front of a logarithm, we can bring that constant into the exponent for the argument of that logarithm. So 2 times the natural log of 2 is the same as the natural log of 2 squared, which would just be the natural log of 4. Now, in this case, of course, any of these answers would be acceptable. These are all the same number, but just illustrating here that you can simplify an expression involving logarithms by using properties of logs. So let's look at another one. In part H, we have the integral from 0 to 1/2 of 1 over the square root of 1 minus x squared with respect to x. So we need to find an antiderivative of this function. So recall that the antiderivative of this function is a little bit tricky. 1 over square root of 1 minus x squared is the derivative of the arcsine function. So here, the antiderivative of 1 over the square root of 1 minus x squared is arcsine of x, which we would then evaluate from 0 to 1/2. And I'll mention some notation that you might see throughout this semester. So the inverse sine function we can either write as sine inverse of x, like this, or some people prefer to write arcsine of x, which we would evaluate from 0 to 1/2. So those notations are equivalent. Now another comment I'll make here, a little word of warning, this notation that we're using for the inverse sine function, this is not equivalent to 1 over sine of x. So the notation sine inverse of x is not the same as 1 over sine x. Recall 1 over sine x is cosecant x, which is not the same as the inverse of the sine function. So just a word of warning there. So it may be beneficial to use this notation, arc sine of x, to avoid making that notational mistake. So let's evaluate this. We would first take arc sine of our upper limit of integration, which was 1/2, and then we subtract the value of arc sine at the lower limit of integration, 0. So to find arc sine of 1/2, we ask ourselves, well, what angle gives us sine of that angle is equal to 1/2, and that would be the angle pi over 6. Sine of pi over 6 is 1/2, so arc sine of 1/2 is pi over 6. Minus, here we have arc sine of 0, which is 0. Since sine of 0 is equal to 0, we know that arc sine of 0 would be 0. So we're left with simply pi over 6. So a little review of a function which has an inverse trig function as its antiderivative. So let's look at another one, part I. We have the integral from 0 to 2 of x squared minus the absolute value of x minus 1. So what makes this one a little tricky is that absolute value expression. So we're not sure in general how to find the antiderivative of an absolute value, but let's think about how the absolute value of a function is actually defined. So recall that the absolute value function is really defined piecewise. So let me make a little scratch work to the side here. Remember that the absolute value function, absolute value of x, is actually piecewise, and it's defined as x as long as the value of x is non-negative. So if you're taking the absolute value of some number which is greater than or equal to 0, the absolute value is just the number itself. For instance, the absolute value of 3 is simply 3. But if x is negative, so for values of x less than 0, the absolute value of x is the negative of x. So in particular, like the absolute value of negative 3 is positive 3, which would be the negative of negative 3. So this is actually defined in this way. So in our example, let's think about how the absolute value of x minus 1 is defined. So here, the absolute value of x minus 1 will be defined also piecewise as simply x minus 1 as long as x minus 1 is non-negative, or as long as x is greater than or equal to 1. Now, if x is some number less than 1, then the value that I'm taking the absolute value of, x minus 1, would be negative. So in order to take the absolute value of that negative value, I would have to take the negative of x minus 1, which would be 1 minus x. So we see that this absolute value function changes its definition at the value 1, which is right in the middle of the interval that we're integrating over. We're going from 0 to 2. So on our interval here, from 0 to 2, our function changes its definition at 1. So we're going to need to split this integral into two pieces. First, we're going to integrate from 0 to 1, and the function that we're integrating is x squared minus Well, let's think about how that absolute value is defined on 0 to 1. So here we said if x is less than 1, so on the interval from 0 to 1, this absolute value function is 1 minus x. So we have an x squared minus 1 minus x dx. And then we will add the integral from 1 to 2. We're going to take the rest of our interval. And our function is x squared minus, now on the interval where x is greater than or equal to 1, the absolute value is defined as x minus 1. So here we are subtracting x minus 1, integrating with respect to x. So let's simplify a little bit. We have the integral from 0 to 1 of x squared minus 1 minus a negative x, or plus x dx, plus the integral from 1 to 2 of x squared minus x, and then subtracting the negative 1 is a plus 1 dx. So let's find the antiderivative of each piece. For our first function, we have an antiderivative of 1/3 x cubed minus x plus a 1/2 x squared. And this antiderivative we're evaluating from 0 to 1. And then we add, for the antiderivative of this second piece, we have a 1/3 x cubed minus 1/2 x squared plus x, which we're evaluating from 1 to 2. So for our first antiderivative, we substitute the upper limit for integration, 1, in place of x, which gives us a 1/3 minus 1 plus 1/2. And then we subtract the value that we get by substituting 0 in for x, which would be 0. Then we are adding, for our second integral, we evaluate at x equals 2, which would give us 8/3 minus 2 plus 2. And then we subtract the value that we get by substituting in 1, which would be a 1/3 minus 1/2 plus 1. So simplifying some like terms, let's see what we have. So here we had a negative 2 plus 2, which will cancel. We have let's group our third terms. We have a 1/3 plus 8/3 minus 1/3. So our plus 1/3 minus 1/3 cancel. That gives us 8/3. Now grouping our other terms, let's see what we have. We have a negative 1 plus 1/2, which is negative 1/2. And then on the end, we were subtracting a negative 1/2 plus 1, which would be 1/2. So our negative 1/2 minus 1/2 gives us a negative 1. So we have 8/3 minus 1, which would leave us with 5/3. So this last example illustrates how we would handle the case of finding an antiderivative of something involving the absolute value. We have to think about that absolute value function as being defined piecewise, and we might have to split our integral into a couple of pieces depending on how that absolute value function is defined on different intervals.